In this lecture, we're going to learn about dynamic casts. And the dynamic casts are a facility we have in C++ to do downstream transformations between our polymorphic types. So if we have a base pointer, for example, we can transform it to a derived type and be able to use it like we use any row object. For example, if we do this kind of transformation, we will be able to call non-polymorphic functions, and this may come in handy sometimes. This is the hierarchy we will be using. Our top class will be animal here. We will derive from this and create our feline class, and we will derive from feline and create our dog class here. If we have a base pointer pointing to a dog object, for example, the most specialized class we can have in our inheritance hierarchy, sometimes we might want to transform from this base pointer to the most derived object here and get the direct most derived object that we can really call anything on. If you remember, with a base pointer like animal here, the only thing we can do is really call polymorphic or virtual functions. But sometimes we want to do much more than this. For example, if we want to call non-polymorphic functions, this is not going to work because the base pointer has no knowledge of those functions. So if we need to do that, explicitly transforming from a base pointer to a derived pointer is going to give us that capability if the actual object we are pointing at happens to have that method. Okay, so this is what we are after in this lecture. We want to be able to transform from a base class pointer or reference to a derived class pointer or reference at runtime. Another way you can take this is to think of the base class pointer or reference as input, and we want to get a derived class pointer or reference as output in our C++ program. And the main benefit of this is to be able to call non-polymorphic methods on derived pointers or references. This is going to be super cool in some cases. Okay, so let's look at our inheritance hierarchy here. The top class is going to be animal, as you see here. It's going to have a single virtual method. It's going to also have a virtual destructor because we know how to do this now. We can derive from this and create our feline class, which is going to be inheriting publicly. It's going to have its own run method, and it's going to declare its own other method, which is not virtual. We can also derive from feline and create a dog class. This is how we do this. And we're going to set up our own virtual method in dog, which is going to be bark. And we can really do anything we want with this inheritance hierarchy. Okay, what we're going to be using as input is a base class pointer or a base class reference, and we set them up here. This is our base pointer, this is our base reference. And we want to go from these and create a derived class pointer or reference that we can use to even call non-polymorphic functions. And we can achieve that using dynamic casts. Here we're going to show you how you can cast pointers. Again, our animal base pointer is going to act as our input, and the output is going to be what we want to get out of this transformation. And all we do is say dynamic cast. We specify a pair of angle brackets. Inside, we're going to specify the output we want to get. And this is usually going to be a derived class pointer. So the base class pointer is going to be within this parenthesis, and it's going to be our output. And this is going to do the transformation, and it's going to give us a result that we're going to be storing in our feline pointer here. And if this succeeds, we will have a valid feline pointer here, and we can use it to call non-polymorphic or non-virtual functions like we are doing here. And this is super cool. Another thing you can do with this is use the result of this transformation in a pointer check. For example, we can check and see if this pointer is not a null pointer. If it's not a null pointer, we can call our non-polymorphic function to it. The result was successful. But if it's null pointer, we're going to fail and fall down here, and we can say that we couldn't cast to a feline pointer. And some of you might ask, how can this transformation fail? Well, if we go back to our code here, we have an animal base pointer, which is really pointing to a feline object in memory. If we try and cast this animal pointer to dog, suppose we want to do this kind of transformation, Try to think about this. This is not going to work because we really have no dog information in this feline object. And if we try to cast this to dog, the compiler will really have no way to do this, and the transformation through dynamic cast will fail, and we will say the message here, meaning that we couldn't do the transformation the user asked for. So here we can do the transformation and transform from a base pointer to a derived pointer, but we can also transform to a derived reference. And I am going to show you the syntax to do that, and it is super simple. We say dynamic cast and we specify our input reference. Notice that this is a reference you have to put in, it's not a pointer, and you specify the output within these angle brackets here. Once you do this, the output of this is going to be a derived reference, and we're going to store this in our feline reference here. Once we do this transformation and the transformation is successful, we're going to be able to call our non-polymorphic function, and this is going to work. But with references, we don't have the luxury to do something like a pointer check because there is no such thing as a null reference. A reference is always pointed to something, and if the transformation fails, we will have some kind of invalid reference. And if this fails, it is probably going to blow up and give us undefined behavior. So you don't really want to do this. I usually don't recommend doing this kind of transformation with references unless you know that the transformation is possible beforehand. What I usually recommend is to pass through pointers, and it is even possible to transform a base reference into a derived pointer, and the syntax to do that is what you see here. Okay, and once we do a transformation to a pointer, if the transformation is successful, we're going to have a valid pointer in here. If the transformation fails, we're going to have a null pointer, and the check is going to draw us here, and we're going to print this message to say that we can't do the transformation here. Okay, again, the cast may fail. If it fails while we are trying to transform to a dog pointer, we are going to fall down here and say that the cast failed. We can also do the same thing through references. For example, if we want to transform this base reference to a derived pointer, and this fails, we're going to fall here because of the check we are doing here. We can do something like this to make our code much safer to work with. And another thing I should really point out is that in practice, casting like this is usually done in functions where you are passing a base pointer or a base reference as a parameter. And in this function, you somehow need to call a non-polymorphic function. So you might do something like this and take the pointer and turn that into a derived pointer. And if the transformation is successful, you're going to call your method. And if the check fails, you're going to fall here and print an error message. You can do something like this with pointers, and we can do exactly the same thing with references. But here, because we want to do this check, we're going to transform our base reference into a derived pointer and call our method on the derived pointer instead. This is going to give us the ability to do this kind of check to make our code much safer to work with. A word of caution here, overusing downcasting is a sign of bad design. If you find yourself doing this kind of thing a lot to call non-polymorphic function, that may be a sign that you should make that non-polymorphic function polymorphic, because that's going to save you from doing this kind of transformations a lot. Just make sure you don't overuse this and do it in a few cases where you really need to do this kind of thing. Now that you know this, we're going to head over to Visual Studio Code and play with this a little more. Here we are in our working folder. The current project is Dynamic Casts. We're going to grab our template files and we're going to put them in place. Let's do that. And we are going to grab the files that make up our inheritance hierarchy. We're going to put those in. We have animal, dog, and feline. And this is going to make up our inheritance hierarchy here. Once we have this in place, we can open this up in Visual Studio Code by dragging and dropping here. And this is going to give us our files. Okay, we have our files in here. We can open up the animal class, which is our base class. We can see that it is really simple. It's just going to have one virtual method, which is breathe. It's going to have a single member variable, which is description here. We can derive from this and create our feline class, which is going to inherit publicly from animal. Feline is going to set up its own method which is non-virtual, and we will have a virtual method called run. We can override in downstream classes if we want to do that. And let's look at the implementation for feline CPP. If you want to do that, you can take a look. It's just going to forward the construction to the base class to build the base part of us. Let's look at dog. Dog is going to inherit from feline, and it is going to set up a simple virtual function called work, and it's going to have a virtual destructor. Now we know that we should really put in virtual destructors if we happen to even have a single virtual method in our inheritance hierarchy, because that's going to make things easier. Now, we want to go to the main CPP file and play with dynamic casts. We're going to remove whatever it is we don't need here, and we can include our most derived class. Let's include dog here. This is going to implicitly include both feline and animal, because this header is going to include its parent, and its parent is going to include its own parent. This is the logic here. We are going to start out by using a simple example here and show you that you can't really call non-polymorphic functions from a base pointer that is managing a derived object. And here we have an animal pointer. It is a base pointer, and it is managing a real feline object in memory. But if we try and call a non-virtual function through this base pointer, this is going to blow up. This is not going to work because we can't really call a non-polymorphic function through a base pointer, because that's not a virtual function. The requirement to be able to do this is for the function to be virtual, and do some feline thingy is not a virtual function that we know at the base level. So this is not going to work by default. And if we try to build code like this, this is going to give us a compiler error. Let's pass this through GCC. We're going to do that. We are going to finish the build with errors, and if we go up, we're going to find that class animal has no member named do some feline thingy. So this is the compiler error here. This is not going to work. If we need to do something like this, one solution might be to do dynamic casts that we are learning about in this lecture here. And the syntax is ridiculously simple. So we can go down here and put in a simple separator to be able to follow these things on our PowerShell window. You can do this if you want. And we're going to do our dynamic cast. For example, if we wanted to do a transformation and transform this to a dog object, this would give us a problem. And let's try and look at this again. We have a feline object here, and we are managing this through a base pointer. And what we want to do is to take this base pointer and turn it into a dog object. If you look at this, remember that we don't really have any dog information in our feline object. This is going to just go up to the level of feline, but we want to transform this to a dog. To make this super clear, let's look at our inheritance hierarchy again. What we have is a feline object, and the information we have really goes up to this level, and we are managing our feline object through a base pointer. This is the setup we have, but we want to do the transformation and turn this base pointer into a dog object. And this is going to blow up, especially if we have any dog specific member variables. This is going to blow up. This is not going to work. If we try to access dog information through what we get through the transformation to animal to dog, we're going to get a crash because we have no such information, and we're going to look at a simple example to really drive this home. So what we're going to do is go back to our dog class, and we're going to put in a simple member variable. We're going to make it private. And for example, we can make this a member variable to keep track of the speed for the dog. We can do this. And we're going to initialize this to 0 by default. And we're going to set up a function which is going to print some dog information. Let's go back to feline and copy the do some feline thingy method. And we're going to do some dog thingy. That's what we're going to do here. I am going to put in this method and adapt it a little bit. We're going to do some dog thingy, and we're going to account for that in the body. But we also want to print the speed for this dog here. So we're going to say speed, and we're going to print this out. Suppose we have this kind of setup in our inheritance hierarchy here. A dog object has some dog specific information. It has an additional member variable, which is mSpeed here. We won't worry about initializing this from the constructor. You can do that if you want. All we really want is to add some extra data at the dog level. And we're going to see that if we try to transform to dog, this is going to give us a few problems. So what we want is to turn this animal base pointer into a dog object. Let's do this. We're going to change this to dog, and the result object we get is going to be a dog pointer. And we want to call the do some dog thingy method on the pointer we get as a result of this transformation here. Let's see what happens. You're going to see that this is not going to give us any indication that we are doing something wrong. But if the transformation here fails, this is going to silently fail and store junk data in our feline pointer here. And here we're going to try and call a method that is going to possibly use some dog stuff on a feline object. This is going to blow up. Again, we don't have dog information in this feline object, and the do some dog thingy method is going to try and print the speed of the dog that we don't really have. We don't have any dog information, so we have no business accessing dog information from this object to start with. So this is going to blow up, and it's probably going to give us a crash. Let's try and build and see what happens. We're going to pass this through GCC like we always do. The build is going to go through. You see that this is going to even blow up at runtime when users are actually using your application. This is super dangerous. We're going to run this and see what happens. You see doing some dog thingy, and it's going to try and print the speed. The compiler is really trying its best, but this is really going to fail. And we are crashing our program. If you go down here and say done, to make sure we know when the program is done, and we try and run our program again, let's pass this through GCC to take into account this thing we have on line 20. The build is going to be good. You're going to see that the computer is going to try and really run this, but it's going to see that it doesn't really have any dog information, and the computer is not going to succeed because we are trying to access this dog specific information really on a feline object, so we are going to get a crash. Again, the message is that these dynamic casts can fail, and we need a better way to do some kind of checks before we call our methods here. And we can do this by just using the pointer we get from this transformation here. So we can say if feline pointer and check and see if we have some valid data in this feline pointer. And if that's the case, we're going to do whatever we want to do with this pointer here. Okay, so this is something we can do. And if the transformation fails, we're going to fall in this else block, and we can put some nice message here instead of letting the user crash at runtime. This is much better in my opinion. So we're going to say couldn't do the transformation from animal pointer to dog pointer because we really have no dog information in this base pointer that we have here. This is something we can do. So we're going to say stdc out. We're going to say stdendl here, and we're going to see what happens. Let's build. Hopefully we're not going to get the crash because we are doing something smarter now. We are checking to see if we have any dog information in this pointer before we call some dog specific method on this pointer here. This is the beauty of this. We're going to clear and run rooster. Now you see couldn't do the transformation from animal to dog, and our program is no longer crashing. It is ending properly, and this is much better. This is what you should aim for. So again, the transformations here may fail, but if we turn this back to doing feline transformation, let's do feline pointer. We're going to change this to feline pointer again, and we're going to do some feline thingy now. We're going to build again, and this is true. We're going to build again, and this is going to build successfully, and it is going to properly do some feline thingy. The build is good. We can clear and run rooster. This is going to work just fine, and our program is going to end properly. So here we just saw that we could do a transformation from a base pointer to a derived pointer, and this is going to work just fine. We can also do the transformation for references. Let's say that here. And we're going to go down and put in a simple example to drive this home. We're going to have a feline object. We're going to set up a reference to it. And if we try and call a non-virtual method on this base reference, this is going to blow up because the base class has no information about this non-virtual method that we declare at the feline level. This is going to blow up. If we try to build our program, we're going to see that we get a compiler error saying no such method as do some feline thing. We're going to see that here. No member named this way at the animal level. This is the compiler error we get if we try to call a non-virtual method through a base reference that we have here. This is not going to work. But we can also do a dynamic cast and transform from a base reference to a derived reference. And the syntax to do that is really here. We're going to set up a derived reference. In this case, it's going to be a feline reference. We're going to initialize this with a dynamic cast transformation. And the result of the cast is going to be used to initialize this reference here. And we're going to be taking a base reference and turning that into a derived reference here. This is the syntax. The output you desire is going to be within these angle brackets, and the input is going to be through this parenthesis here. If this succeeds, we will be able to call our method here, and this is going to work just fine. Let's try this out. We are going to put in a separator to be able to follow these things. Let's put that at line 24 here. This is going to do. And we're going to try and build our program. We're going to pass this through GCC. The build is good, we can clear and run Rooster. Now we're going to see that we are doing some feline thingy through a reference. And this is super cool. We can do this. You can do this kind of transformation here. And at the end, you see that we are calling our destructors on our objects. And this is a good reminder that we didn't properly release the memory on this animal pointer that we had. So we are going to go down at the end of the program and release that memory. This is good practice. And hopefully you can see how easy it is to forget to release some memory that you allocate for with the new operator. This is a good learning experience here. But we're going to fix this problem. We're going to say animal1 and we're going to release the memory. Now if we run the program, we're going to see that we are releasing two objects when the program ends. We're going to clear and run Rooster, and the destructor is going to be called 2 times. Once for this guy and a second for this guy. This is what we want. And you see that because we have virtual destructors in our classes, we are destroying at each level. So here we are destroying at the feline level and we are destroying at the animal level. And this is going to properly release the memory from our inheritance hierarchy here. So now you know that you can do a transformation of references using dynamic casts. But with dynamic cast, we have no way to check and see if the transformation was successful. Again, if we try to turn this into a Doug reference, we can do that. And we're going to say Doug reference here. And we will try and call the do some Doug thingy method. This is not going to give us an indication of a problem, but this is going to crash at runtime because we don't really have any Doug information in our original feline object here. So if we try and transform this reference into a Doug reference, this is obviously not going to work because we have no Doug information in this to start with. Let's build and show you the problem. The build is going to be good, so we can clear and run Rooster. You're going to see that we are going to terminate our program with a bad cast, and this is going to crash. You see that we don't get to the point where we print done, and we are not even going to get a chance to release the memory that we have allocated in this main function. Hopefully you can see that this is really bad. So with references, we have no way to check and see if the transformation was successful. And this is a limitation. That's why in most cases, I usually do my transformations through pointers. And there is a way you can even turn this base reference into a base pointer. And I am going to show you how you can do that. So we are going to go down here and try to change things a little bit. We are going to say doing proper checks with references. And we're going to put in a piece of code to play with us. And what we're going to do, we're going to take the base reference and turn that into a base pointer. This is the syntax here. Again, the input is a base reference, but the output we desire is a base pointer, and this is possible in C++. This is going to work just fine. Now, we are going to go on top and comment this problematic transformation we just tried to do, and we're going to try and build and see if this is actually working. If this transformation succeeds, we're going to do some feline thingy. If it fails, we're going to say couldn't cast to feline reference, and we're going to say that we are sorry. This is a good output message. If we get something wrong, we're going to build this with GCC and see if this actually works. The build is good. We can clear and run Rooster. You see that this is working just fine. We're going to hit the end of the program and we are going to destroy our objects here. This is super cool. But if we try and do the transformation and transform to a dog object, even if we know that we don't have any dog information in this object that we are referencing to start with, we hope that we're going to get a good message and the program is going to end properly. We're not going to get a crash. So let's make sure we are transforming to dog here. We're going to pass a dog pointer as our output, and we're going to store this as a dog pointer, even if the name is still feline pointer. Hopefully this is not going to confuse you. Even if this is named feline pointer, it is a dog pointer here because we just want to see if we get the error message that we have here. So we are turning this reference into a pointer, and the benefit of this is that a pointer can store null pointers, and we can use this to our advantage to check and see if the transformation here was successful. If it was successful, we will call some dog thing method. Let's say that here. And if this fails, we're going to say that we couldn't transform to dog, and this is going to give us a nice message and our program is not going to crash. We're going to build this again with GCC. The build is going to be good. As you see here, we're going to clear and run Rooster. Now you see that we are saying we couldn't cast a dog reference and our program is not crashing. So if you have a reference to start with and you want to do some proper checks after you do the transformation to a derived pointer or a derived reference, this is the best of both worlds. You can do something like this and your program is going to be much safer. The last thing I want you to see is that these kinds of dynamic casts are really useful if you are passing base pointer or base references into functions. And here I am going to put in a bunch of functions. The first one is going to take a base pointer. The second one is going to take a base reference and it is going to say do something with animal pointer and do something with animal reference. And inside we're going to do our thing here. We're going to take the animal pointer, turn that into a feline pointer, and we're going to do our proper check and we're going to do some feline thingy. If the transformation was successful, we can do something like this. We can also do exactly the same thing with references. We're going to take our input reference. We're going to turn that into a derived object and we can call our method on this pointer. And we're going to do proper checks because we have a pointer which has a concept of null pointer that we get if the transformation here fails. This is the setup we can use in our C++ programs, and we can use these methods to get derived pointers that we can call even non-polymorphic functions on, and this is going to work really well. So we can go down and comment out everything, I guess, to make this super easy to follow, but I don't think we need to comment out everything. We can just comment out what we just did here, and we're going to be reusing the reference we have here and the pointer we have all the way to the top. So we're going to go down and put in a separator here. We can do that. And because of this separator, I don't think we even need to comment things out. We can remove our comment and leave the code in because I want you to see that super easily. And we're going to call our functions here. We're going to say do something with animal pointer and we're going to pass in animal one, which is a pointer. And we're going to say do something with animal ref. We can do something like this. And we're going to pass in animal ref. We have this reference here and we can do something like this. You're going to see that this is not going to give us any kind of problem and it is going to work just fine. Now let's build. We're going to pass this through GCC. The build is going to be good. We can clear and run Rooster. And down here you see that in function taking base pointer, doing some feline thingy, in function taking some base reference, doing some feline thingy, and this is working really fine. This is what we want in our C++ programs. This is really all I wanted you to see in this lecture. Hopefully you didn't find it confusing. Again, the message is that you can do dynamic casts to transform from a base pointer to a derived pointer or to transform from a base reference to a derived reference as we did right here. But transforming to a derived reference has a drawback in that you don't have a way to check and see if the transformation was successful. So if you want to be able to do checks, you can do something like this and turn a base reference into a derived pointer. And then we can check and see if the pointer is not a null pointer. If it's a null pointer, we will know that the transformation failed and we will print a good error message. If the transformation was successful, we will have a valid pointer in here and we will call our derived non-polymorphic method on our pointer, this is going to work really fine. The last thing I want you to see before we wrap up this lecture is that dynamic casts are only going to work with polymorphic inheritance hierarchies. So for example, if we try and turn a double into a string, obviously that's not going to work with a dynamic cast, but let's try and do that to really show you that this is going to give us a problem. We're going to say stdc out and we're going to put in a separator here. And we're going to set up two variables. One is going to be an int, for example, and we're going to say data. We're going to put in a 45. And if we do a dynamic cast to an std string, for example, that's not going to work. We're going to say std string data str, meaning that this is a string. We're going to say dynamic cast. Let's say we want to turn this into an std string, for example, and the input is going to be our data. If you're trying to do something like this, this is going to blow up. You see that even Visual Studio Code is giving us a squiggly line, so this is not going to work. Just make sure you use dynamic casts in an inheritance hierarchy that supports virtual functions. This is the design purpose for the dynamic casts. If you use this outside this context, you're going to get undefined behavior or even compiler errors if you are lucky. Let's try and build and show you this. We're going to pass this through GCC, and we're probably going to get an error saying that we can't transform from an integer to a string. For example, let's go here, cannot dynamic cast. So basically it is saying dynamic casts are meant to work only with pointers or references. But even then, let's see if we can transform from an int pointer to a string pointer. Let's try and do that. Let's say we want to turn the address of data, or let's set up a pointer to be explicit. We're going to say data ptr, and we're going to initialize this with the address of data. We can do something like this. And we're going to cast data ptr to an std string pointer. Let's see if we can do this, because it is meant to cast between pointers and references, but you see that this is even not going to work. So you shouldn't really do something like this if your input and output are not part of the same polymorphic inheritance hierarchy. Again, dynamic casts are meant to cast from base information to derived information, and the input and output must be part of the same polymorphic inheritance hierarchy. This is the information I am trying to convey here. So this is bad. Don't do something like this. If you do this, you're going to get undefined behavior, or you're even going to get a bunch of compiler errors if you are lucky. This is really all we set out to do in this lecture, showing you that you can use dynamic casts. We are going to stop here in this lecture. In the next one, we're going to show you what happens if you try to call a polymorphic function from a destructor. Go ahead and finish up here and meet me there.